Right, okay, hello all. I'm just going to talk you through drawing a Born-Haber cycle so that when you come into your lesson tomorrow, you'll have a clear idea of how we do that and what the point of it is, so that we'll be able to move on a little bit more swiftly than if I was showing it to you in the class. Okay, so the Born-Haber cycle is related to ionic compounds, the formation of ionic compounds, and is a manifestation of the law of conservation of energy, because we're talking about an ionic compound that can be formed using two different routes. And as we know from what we learned about Hess cycles and using Hess's law, it doesn't matter which route a chemical reaction follows, the energy change will be the same. Okay, so we're looking at this same idea here. Right, okay. So let's start with sodium chloride. Okay, and I'm just going to quickly flick through this. Right, so we've got the normal standard Born-Haber cycle format here. If you notice, we've got sodium chloride at the bottom, which is our solid ionic compound. And if you look, there are two arrows that point down to this baseline. Enthalpy change of formation on the left, and enthalpy change of lattice energy of formation on the right. So that indicates that this ionic compound can be formed using two different methods, effectively. One is using the elements in their standard states. We've got sodium here as a solid, and we've got chlorine here as a gas. So that's one way, or the other way it could be formed would be from its gaseous ions. So here we've got sodium +1 and chloride -1. So when you're drawing a Born-Haber cycle, it's best to use these same steps every time, and then you know that you won't have forgotten anything. Okay, so we have enthalpy change of formation. So the best way to start is to draw this line and put your elements in their standard states. And then you have an arrow coming down showing enthalpy of formation. That arrow coming down is indicating that energy is being released. So, well, if these two elements come together to form sodium chloride, we would expect energy to be released. Okay, now if we're going to go the other way, so that's one route, okay, the direct route. If we're going to go the other way now, we have to form our ions first. They're up at the top here, or the sodium ion is up at the top here with an electron, and here we've formed the chloride ion. But first of all, before we can do that, we need to put some energy in, and that's what this arrow indicates here, so that we can atomize these two elements. At the moment, we've got solid metal, sodium, and we've got molecules of gaseous chlorine. So we put energy in and we atomize our two elements. If you notice here, the state has changed for sodium. It's become gaseous because we've put the energy in and split up our metal, and it's now in gaseous atom form. The chlorine, obviously here it was in molecular form, half of Cl2. Now we've got Cl and still gaseous form. Right, so we've got atoms now. We now need to turn our atoms into ions. So the first ion that will be formed will be the metal ion. So ionization energy, enthalpy change of ionization energy, again energy going in, you can see that from the arrow going up, forming Na+, gaseous. Very important that the states are put in. You would definitely lose marks if you don't have states on your Born-Haber cycle, plus an electron because it's lost the electron, plus still our chlorine atom at this point. Okay, now chlorine, of course, accepts an electron, so we don't have ionization energy involved in the formation of a chloride ion. We call it electron affinity, the enthalpy change of electron affinity. So chlorine accepts the electron that sodium has released, and energy to do, as that happens, energy is then released. So we can see that the arrow coming down indicates that. So we've released energy. We've now formed our two gaseous ions, sodium and chloride, which then come together, releasing more energy to produce sodium chloride, the solid. Yeah. Right, now, so the important thing is, how can we draw our own Born-Haber cycles and use the standard format? So I've just clicked through here the labels that we would put on at each point on the Born-Haber cycle. So at the bottom, we've got our ionic compound as a solid, and we have the elements in their standard states, gaseous atoms, metal ions plus electrons, and non-metal atoms, and then our gaseous ions, both gaseous ions here at this point, and then lattice enthalpy or lattice energy of formation. Okay, now recognize from this is the equation. So this enthalpy of formation, this arrow coming down, is equal to the sum of all the other enthalpies. So this will be positive, this will be positive, this will be negative, this will be negative. Add them all together and that will come back to enthalpy of formation. Pretty straightforward, huh? Okay, so let's have a go at doing a calculation. So you've got your enthalpy of formation is what we're looking for. As we just said, enthalpy of formation is the sum of all the other values. So take a second, maybe pause the video, do the calculation, and then you can move on and see if you're right. Okay, so here we are, enthalpy change of formation, adding up all these values to give us minus 411 kilojoules per mole. Okay, so you notice there are two values here because we've atomized two different elements, yeah, and one value in each other against each other arrows. Okay, right, so magnesium chloride, a little bit more complicated, this one. Again, we start with our ionic solid at the bottom on the line, and the elements in their standard states. Chlorine is a gas, magnesium is a solid. This time we don't need to have half chlorine because magnesium forms a 2+ ion, yeah, MgCl2. Okay, so we go through the same format. We atomize our elements, yeah, and then we ionize the magnesium. Now there will be two values here because we've got two ionization energies to form Mg2+ plus 2 electrons, and then we're going to have two values for electron affinity because we're forming two chloride ions, and then lattice enthalpy of formation. We'll put these values in and you'll see what I mean. So here, 2 times 121, we're referring here to the chlorine, yeah, being atomized. Ionization energy, two values, the first ionization energy, second ionization energy, to ionize magnesium to 2+. And here 2 times minus 364 because we are forming two chloride ions. Now notice that here we're looking for the lattice energy of formation. So our equation said that delta H of formation was equal to the sum of all the rest. So we're going to have to rearrange this equation slightly so that we can come to find enthalpy change of lattice energy. Okay, so here we are, minus 642 and all the other values plus enthalpy change of lattice energy. We want this on its own, so obviously we're going to have to bring these values across and change the signs. And hey presto, there you go. Minus 2492 kilojoules per mole. to be really, really careful here with the signs. Absolutely crucial. Okay, so hopefully you can now have a look in your textbooks and read through the chapter, maybe make some notes, come back and have a look at this video of the PowerPoint, and then tomorrow I will clarify any points with you, but we should be able to get straight in to drawing Born-Haber cycles. Thank you and good night.